Hello everyone, welcome back to the course on LLMs. So we were discussing alignments of large language models, and in the last class we discussed how human generated feedback can be injected to this model for further refining things, right? So specifically we discussed that we have a policy model, right? The policy model is the LLM that you want to refine, that you want to fine tune, right? And then this policy model will generate certain output. This output will be scored by a reward model. This reward model itself is another LLM, right? So it will produce a reward, and based on this reward we will further refine this policy model, right? We also discussed that only reward maximization is not enough, because what happens if we only maximize the reward, what would end up happening is that the policy model will start hacking the reward model, meaning that it will start producing such responses for which the reward model will produce higher reward values, right? But the responses may not be realistic. For example, the policy model will start producing a lot of emoticons, right? It will start producing sentences which are verbose, lengthy, and so on and so forth, not to the point, and so on and so forth, which you do not want, right? Therefore, to address this reward hacking, this loophole, what you do, you have another component in the objective function which you want to minimize. And what is this component? This component is basically the divergence, scale divergence between the old policy and the updated policy, right? The old LLM and the updated LLM, right? So you do not want the updated LLM to be very, very far from the starting LLM, right? So we discussed maximizing the reward, which is the expected reward that you obtain given a policy. So the policy model is theta. So this is parameterized by theta. You essentially sample, given a prompt X, this policy model will generate a Y, and this for this Y you have this reward. Okay, so for example, X is the prompt. The prompt is where is Taj Mahal located, and let's say the Y is the response. Let's say the response is Taj Mahal is located in Uttar Pradesh, or Taj Mahal is located in France, and so on and so forth. And based on that, you give high reward or low reward, right? And this second term, right, this term is essentially the scale divergence between the updated policy model and the reference policy model. Okay, so pi theta and pi ref. So reference LLM, reference policy model is the one from which you started your reward maximization process. Okay, and then these two components will be combined. So you want to maximize reward and minimize the scale divergence, and there is this beta scaling factor. Now this lambda essentially is responsible for scaling these two components. If you want to give more weightage to scale divergence, you increase the value of lambda, and so on and so forth, right? So this we discussed. So now the question is, or given this regularized reward maximization, why this is regularized reward? Because this component, you can think of this as a regularizer, right? This is your objective and this is your regularizer. So regularizer essentially tries to balance both these things. So this regularized reward maximization will be used to further refine the policy model. Policy model is the LLM again. The policy model is the LLM that you want to rectify, you want to refine. So how do you do in practice? So given a prompt, let's say the prompt is write a poem. You have this policy model pi theta. The policy model will generate n number of poems. For each poem you calculate the reward using reward model and the scale divergence, right? So for every response you have the reward and the scale divergence, reward and the scale divergence, right? And since this is expected, right, what you do, I mean, it's not possible to calculate expectations. So what you do, you essentially sample several such responses from the policy and you make an average of this, right? And this is going to be your total reward, regularized reward function, which you want to maximize, right? Now, in order to maximize this, so through this maximization process, you will essentially learn this theta, right, which is our main objective. Your objective is to basically define the parameters in the policy model. So when you have this kind of picture diagram, what is the way to essentially do this kind of maximization? Let's say this is some average, this is some loss, or sorry, in this case this is essentially the reward maximization objective, right? You calculate the partial derivative of this. This is you do a normal gradient descent, right, with respect to all the parameters present in the system, right, by taking the derivative, partial derivative of the objective function with respect to parameters. The problem here is you cannot use the traditional, the vanilla version of gradient descent here. Why? Think about it. The reason is this part. Okay, this is highly non-differentiable, because here what you are doing, you are generating multiple responses. You are basically sampling multiple responses. You are generating multiple responses, and this is non-differentiable, highly non-differentiable. Okay, this is not one sample, this is multiple samples, right? So standard gradient descent algorithm won't work here. So we need some other ways to essentially address these issues, right? So let us see. So this is something that we'll discuss today. So our regularized reward looks like this. So this is our reward, this is the KL divergence, and this is the expectation, right? Let us denote this term by R sub x xy, right? So essentially you are maximizing this R sub xy. Again, maximizing the regularized reward ensures that high reward outputs as decided by the reward model. So the outputs will have high reward because of this term, and outputs that have reasonable probability under the reference model. Okay, that will be taken care of by this factor. So under the reference model, it should not be very different. Okay, so now let's look at how to maximize this. So we will use some algorithm called, and this is a very straightforward algorithm in reinforcement learning. If you know RL, you may have heard of this term, this algorithm called REINFORCE algorithm, right? So let's again relook at the objective function. So the objective function that I mentioned in this slide is this one, expectation of this one. Okay, now so this one I need to maximize, so I need to take the gradient of this with respect to theta. So gradient of this, and this is expectation. So essentially it means, what does it mean? It means that you generate a sample output, right, from this policy model, which belongs to all possible sample outputs that the model can generate. One such sample output is y, and the probability of this sample output is this one, right, and this is the reward. Okay, so if we do not want to use this expectation, you can unfold it in this way. So given sufficient number of samples which are part of the output set, you take each of the samples one by one, and this is my probability, and this is my reward. Now think about it. This reward is fixed with respect to theta. Theta is the parameter of your policy, and this is my reward model, and this reward model generates R of S, right? And so when I take the gradient of this with respect to theta, this is constant, right? Therefore when I move this gradient, when I move the derivative inside, this will be the part. okay, and this will be separated. This is not a part of this this gradient, okay. So now think about it again. So this is exactly the one that we just derived, okay. uh, Del theta pi theta y given x reward x comma y, okay. So now exact computation of this gradient is intractable because you do not know the output space, you do not know this output space y, because the LLM can generate infinite number of responses, right? So can we approximate it? In order to approximate this, I need to rewrite this expression in terms of some sort of expectation, okay. So I need to rewrite this in terms in terms of expectation, which would look like this. So what would be the exact expectation formulation that we will discuss, okay. So this is the desired form that we wanted to that we want to produce from this equation, right? Okay, don't worry about all these equations, okay. This is very straightforward. I will explain these equations one by one. So what I will do here, I will do some sort of log derivative tricks, and this is a very old trick, okay, nothing fancy. What does it say? It says that you take the derivative of this. What is this term? Why this term? From where this is coming, I will explain later. Let us assume that there is a term, this log of pi theta y given x, and you are taking the derivative of this. So this will be 1 by this one times derivative of this one, log of z, right? 1 by z and then dz dx, okay. So now you move this here, okay. So if you move this here, then you will have this term, which is this, and this times this here, okay. Now why this is important? Because why I derived this? Now look at the expression that I had earlier, okay. This is this one, okay. Y given capital Y, right, pi theta right, and then we also had derivative with derivative of this pi theta y given x and rs xy, right. So this is the expression, okay, derivative of, right. So what I will do, and then this r term, okay, I will replace this by this, okay. You replace this here, okay. So now if you look at this very carefully, this is actually an expectation, right. This is probability, this is sample, right, expectation. So what is this expectation? This is this expectation. So if you move this part separately, if you keep this part separate, if you only focus on this, this is nothing but expectation, and you can write in this way, right. So expectation of this, right. So essentially you sample a y from the policy model, then the reward of that y, and then the derivative of the log of the reward. This is the expression. So I wanted to get an expression like this. From here, that I got. Okay, so now we have this expectation, right? So let's see. So again, let's look at the same figure. Prompt, policy model, all these responses are generated, right? You have reward model gives a reward with these are the rewards, right? And then we have, so we need essentially two terms, the reward and the derivative of the policy, right? Derivative of the policy model, given this prompt and this y. So this is this part, right? Poem 1 given x is the prompt, poem 2 given x, and so on and so forth, right? Then what you do, you take the average, right? And why this is called Monte Carlo? This is again a fancy term. Whenever we use sampling as a replacement of expectation, we use Monte Carlo term. Okay, then we average and then we back propagate. So, but the game is not over yet. A long way to go, by the way. So just started. So if you think of this response, right? This response, poem 1, for example, this is y. Okay, and this response constitutes multiple words. Okay, a1, a2, dot dot dot, at, multiple tokens, right? So this is the response, and I am calculating the reward of the entire response, right? The entire response. This is very important to remember. I'm not calculating the reward for every token in the response. This is the entire response. So it means that I need to wait till the end of this response generation, right? And then I'll be able to calculate this reward, right? So once the response generation is complete, I give it to the reward model, and the reward model will generate the response value, right? So nevertheless, so if you look at this term again, right? Pi log of pi theta y given x, log of pi theta y given x. Y is essentially a1, a2 dot dot dot, at. So what you can do, you can right? So you can actually think of it as a cumulative cumulative gradient, right? For every token. So this is essentially log of, let's say Taj Mahal is in UP, right? So log of the policy Taj given, right, the state. And what is the state? The state is essentially the prompt and the responses generated so far, right? So this is this plus log of pi theta Mahal given, so this is S2, right? This is S1, this is S2. What is S2, by the way? S2 is the prompt. Where is Taj Mahal located? Prompt and Taj, right, together, and plus log of, right, is S3. What is S3? Prompt Taj Mahal, right, and so on and so forth. So this is this, right? And we move this gradient inside, right? We move this gradient inside. You can also move this reward inside, right? So this is my compact version. Again, if you look at the reward part carefully, there is no t involved, meaning that this is independent of every token in y. This is only that this reward is calculated for the entire response. Okay, this is written here. For every token, you use the same reward that is calculated for the entire sequence. And now this is the implementation of this reinforce algorithm. This is the prompt. Where is Taj Mahal? Assistant colon Taj Mahal is in Agra, right? So the policy model, essentially the policy model generates this, right? And you get reward this reward value R, right, for every token. Now for every token, now you calculate this log probability, right? Every token you calculate the log probability. States are different, by the way, okay? And then you take the sum of all these rewards, right, and then you backpropagate, okay? But here is the problem. The problem is, in order to find the contribution of the word Taj here, right, I'll have to wait till this, number one. Number two is, let's say the model produces that the Taj Mahal is in France, right, which is wrong. Therefore, a negative reward will be generated. So that negative reward will also impact the word Taj, because the same reward will be used for all the tokens separately, right? But this should not have happened. Why? Because the word Taj is correct, right? So we should not use the same reward for all the tokens present in this response, okay? So how to address this? Now what I mentioned is basically written here. The reward at token Taj depends on the tokens generated in the future. If the model had generated Taj Mahal is in Paris, the reward would be negative. The probability of generating Taj would be decreased, right? If the model had generated Taj Mahal is in Agra, reward would be positive and the probability of generating Taj would be increased, right? This variance in the reward leads to unstable training, obviously, right? So to address this, what we'll do, we'll take the average reward, this is very important, the average reward over all likely sequences that generate Taj for the first token. What does it mean? It means that you look at all the responses generated by the policy model which starts with the word Taj. Taj Mahal is in Paris, Taj Mahal is in UP, Taj Mahal is in Lucknow, Taj Mahal is in West Bengal, whatever responses that the model generates given the prompt, of course, right? And then you calculate some sort of reward, right? Some sort of cumulative reward for the word Taj. And this is called Q function, okay? Some of you may know reinforcement learning. Now this is essentially a very popular method in reinforcement learning. So as you see here, I use this Q function, okay? Now here, instead of using R, I use Q function, which is essentially a function of the state and the current action, right? What is the action? The action is the token that you generate. So here you use this Q function. Now in this case, the state is S1 and the token that you generated Mahal, right? Here the state is S2 and the token you generate is, and so on and so forth. Okay. Now what is this Q function? So the Q function, intuitively, this is average reward of all likely, all likely sequences that start with Taj, right? So you look at all sequences, again hypothetically, you look at all sequences given the prompt, you look at all sequences starting with Taj, you calculate the reward of all the sequences one by one, right? And then you take the average of this, and this will give you some ideas about the the likelihood of of generating the token Taj. Okay, so let us again discuss Q function mathematically. So Q function, I wrote this thing in the slide so that you read and you remember. The Q function for a state action pair is the average discounted cumulative reward received at the state after taking, it is repeated, after taking the specific action. Okay, I'll explain. So Why average? Because I will take multiple such for such actions, and then I'll take the average or some expectation, right? Why this is discounted? This is discounted because what it will do, let's say you generate Taj Mahal is located in West Bengal, right? So, and you want to calculate the importance of or likelihood of the word Taj. So the word Mahal will impact more towards this likelihood. The word is will impact little bit less towards this the word Taj, towards this likelihood, and so on and so forth. And the word West Bengal will essentially impact least towards the likelihood of Taj. It means as we move on in the sequence, the importance of those words towards the current state action pair will reduce. And we captured this using this gamma discounted factor. Okay, so gamma is a discount factor. So you see that the Q function of the state action pair is expectation of the reward of the first state action plus gamma of the second state action, right, plus gamma square R is t plus 2 a t plus 2, right, third state action, and gamma square, gamma ranges between 0 to 1, let's say gamma is 0.9, so this will be 0.9, this will be 0.81, and so on and so forth. So the importance of this will reduce, okay, and so on and so forth. So therefore discounted. Average, why average? Because we take expectation here. Why cumulative? Because we take the sum of all the rewards. So cumulative reward received at the state. Okay, so what it is doing, given the model theta, you generate multiple such responses of size, let's say size t, okay, from the state st. Let's say st is the current state for the word Taj, right, and action is the word Taj. And what are these sequences? The sequences can be Taj Mahal is located in West Bengal, Taj Mahal is located in Agra, Taj Mahal is located in Mumbai, and so on and so forth. These are all sequences. Now for every sequence you measure this cumulative reward, cumulative discounted reward, and you take the average. So this is Q function. Q function is a function of the state action pair, whereas the value function is a function of the state, only state. So what is value function? Value function is the average discounted cumulative reward received after reaching that state. Okay, so this is not a function of action and state, by the way. So what's the difference between this equation and this equation? Only this part. Okay, so in order to generate the next state, next token, my state will be st plus 1. You generate Taj, right, which is my at, okay, and you have this prompt. The next state is so this is my st plus 1. Okay, st was this one till this part. Okay, so Q function, if you think of it carefully, if you look at these two equations carefully, Q STAT is the reward STAT, right? The reward STAT, and sorry, this should be t plus 1. This should be t plus 1. Okay, this should be t plus 1. Why? Because Vt plus 1 will start from t plus 1. Okay, this t, this is also t plus 1 will start from t plus 1, right? And what is, so to calculate this q, I need the reward at t and then the value in the next state. Okay, so if you make some adjustment, now you can use this q function here in the reward part. Okay, but it turned out empirically that this q function is not enough. I need some other function which is called the advantage function. What is the advantage function? Advantage function is basically q function minus the value function for stability, for better stability. Okay, so advantage function captures the contribution of the action over an average action at the same state. Now, if it's very straightforward, okay, if you look at this very carefully, okay, it is essentially the contribution of the action, okay, over all possible actions that you can think of at that particular state. So once this advantage function is calculated, right, now you replace this part which was earlier a q function, before that it was reward, right, then it was q function, now this is advantage function. So the advantage function, you replace all these rewards by advantage function, okay, and then the remaining part is straightforward, the same process. So now this is called reinforce with advantage function. Now how do we implement this thing in neural network? So I need to learn this value function, right? It's a value. So what I can do, on top of every embedding of the token, right? We have all these tokens. Now corresponding to every token, we can add a linear layer. Now this linear layer will essentially serve. So this linear layer will learn. Let's say this is parameterized by 5, and this will learn the value function, right? Now, how do you learn this value function, by the way? Because we need some sort of objective function, right? So what is my objective function? So given the input x, we sample a response y, right, from the policy model. I have this linear layer which is parameterized by 5, which is responsible for calculating the value, right? And what is my ground truth value? The ground truth is essentially the reward. What is reward? So given this, so I have this reward model, right? So given this response, right, I can calculate the reward, the cumulative reward, right, discounted cumulative reward, which is this one, right? The entire response is known to me, okay, and this is called the reward to go. And then my task would be to essentially move this value towards this RT, right? So I will minimize this mean square error. So minimize over all token the value and the reward difference, right? And through this, I mean when we backprop, I will also update the linear layer which is responsible for value function. Okay, so this is my vanilla policy gradient method. So we sample, given a prompt, we first sample a batch of prompts, right? B. Now given a prompt, you sample outputs y, right? For each y, which is essentially a1 e2 dot dot at, you calculate the reward rt for every sequence, for every token at, right? Then you calculate the this is this part, okay? Then you calculate the cumulative discounted reward rt, right, which is this one. Then you compute the value and advantage function AT, right, that you already discussed, right. So I will get Q from R, I will get V from the linear layer. From there I calculate the advantage function, and for every token, then what we'll do, we apply the reinforce method, right, with this advantage function. This is my reinforce method, right, this is my reinforce method with advantage function, and we basically use to essentially train the value function, right, the linear layer that I mentioned, the linear layer. I will calculate the MAC, and this will help me get the parameters fine-tuned in this linear layer. Okay, that's it. But there are still some problems. Okay, so what are the problems? The problem is, if you look at the reward carefully, this part carefully, what we are doing, for every updated policy model, I am generating its corresponding response. Okay, isn't it? If you look at this algorithm here, for every updated policy model, so theta gets updated. For every updated policy model, I need to generate a response. From the response, I will calculate all these things, reward, advantage function, and stuff like that. Now, after every update, if you start generating things, that would be time taking, right? So can we do this thing beforehand? Okay, so this is the idea. The idea is, so this is my reward function, right? What I will do, so first let me let us expand this expectation in terms of summation, right? So this will be my probability, and this is the reward. What I will do, let us use an old model which is theta k. Theta k is the old model, right? So I will use a term here which is the old model and the old model. Essentially this will cancel out, so I add this term. Okay, and then I move this term here, I move this term here and this term here. So pi theta k will come here, pi theta will go here, and then the reward, right? So now I am doing this expectation, calculating the expectation with respect to the old model. So it means that given a prompt from the old model, I will generate responses, okay, and I will measure the probability of those responses from the new model and from the old model. So I don't need to generate these responses from the new model. I will use the old model, generate responses, calculate the probability with respect to the old model, which is the denominator, with respect to the new model, right? And then I have the reward. So this can be addressed. Okay. And this component is called importance weight. Okay. So this is the reinforced algorithm with importance weight. So I've been modifying this algorithm, right, again and again. So now, along with the advantage function, I have the importance weights. We are almost done. So in PPO, now this is reinforced algorithm. In PPO, proximal policy optimization, it turned out that these important functions, this importance weight, these important weights can change drastically. If you do this thing for a specific batch of prompts and some fixed output, you will see a major change in terms of in the importance weight values. So we can bound it. We can bound it between 1 minus epsilon and 1 plus epsilon. What does it mean? It's called PPO-CLIP. What does it mean? It means that if the advantage function is positive, then I will take the mean of this and this. So I clip. I don't allow this importance weight to be greater than this one. If the advantage function is negative, then I will take the max of this and this. Okay, so I will not allow that the importance weight to essentially go below 1 minus epsilon. It's a tricks essentially to make this thing stable. Okay, so what is my current algorithm? This is PPO-CLIP, batch of prompts. We have for each prompt we have samples. For every sample we calculate the reward, right? For every token in the sample we calculate the cumulative discounted reward, we calculate the advantage function, and then we use PPO-CLIP, okay, with the advantage values computed above, and we use MSE for training the linear layer for value function. Okay, so things to remember: log derivative trick is very important, right? Log probability of the tokens should be weighted by the advantage function. Importance weights should be used, right? And importance weights should be clipped in PPO. Okay, that's it. So this is about aligning the model, aligning the policy model with human feedback. Reward model is used to generate the reward. Reward model is trained with human feedback, and reward model will help update the policy model. Okay, with this I stop here, and then in the next lecture we'll meet again. Thank you.